Hello AP Chemistry and welcome to 14.5 covering temperature and rate. So this is a little figure from your guys' textbooks, right? Showing, right, that as we increase the temperature, we increase the rate of the reaction. So let's talk about what that means, right? Thinking about the fact that rate is a measure of change in concentration versus a certain change in time, right? So if we look here, right, if we increase the temperature of the water, and thinking back to what we talked about at the very beginning of the chapter, if we increase the temperature of the water, what are we doing? Right. We are one, increasing the number of collisions, and then two, increasing the energy per collision. Therefore, we get an increase in our rate, okay? Because we've changed those two basic things that have to happen in order for a reaction to occur. Now, as we increase the temperature and we increase the rate, what that means is we're producing more product at a faster or in a shorter amount of time, right? More product, shorter amount of time, which then by default means that the reaction ends more quickly, right? If we're producing more product faster, right, the end result of that is that my reaction is going to be done faster, okay? And so that's sort of, what the point of this is. Other things to think about when we're talking about temperature and rate, right, this is kind of what we're talking about. So this is going back to fraction of molecules, right? Each graph represents the same total number of molecules of a given sample, right? As we increase the temperature, we see that on average, going back to what we talked about in kinetic molecular theory, on average, our molecules have a higher kinetic energy, right? Meaning, if we look here, right, more of them have higher kinetic energy than before. The kinetic energy is what we're using to surmount the activation energy, right? Which means that the point is that as we increase the temperature, a larger fraction of molecules has the energy needed to overcome the activation energy, okay? Because again, that's what we're talking about using our kinetic energy for. The last thing to think about, which we talked about at the beginning, right, is the rate constant K, okay? The rate constant is temperature dependent, and what we see here, right, is that we increase the temperature, we also increase the rate constant, which is another way that we can look at the rate of a reaction increasing, okay? Now, a little bit of new terminology, right? We've seen this graph before. We've talked about the change in energy, which is based on the fact that it's a state function going from here to here, right? Activation energy, that's what we need our kinetic energy to overcome, right? But just to add a little bit of more detail, right? We would count this peak as our activated complex, right? Or our transition state. So that peak is referred to as the activated complex or the transition state, right? And that this is my reactant, right? And my reactant is changing on the way, and this is like the highest energy form of it, right? This is where we put all of our energy in to reach this specific place, right? Where the reaction is just about to happen, and then, right, the reaction actually happens in the forward direction and energy is released, okay? And so this point would be known, this is where the activated complex or the transition state exists. Note that that is a very fleeting state, and there are things that we can do to a molecule to sort of make this state last longer so we can keep track of it, because knowing how a reaction occurs is really useful in the long run in terms of how we can optimize our percent yield, for example, right? But it is a transient thing, right? Not something that is easy to study. Okay, finally, that brings us to the Arrhenius equation, which allows us to put some numbers on our activation energy, which we've been talking about for ages, without any actual numbers, okay? So if we look here, right, this is our rate constant, K, right? Natural log, or E, not natural, anyway. R, note that since we're talking about EA is an energy term, that means this R is going to be the one that includes joules, right? So 8.314. Temperature in Kelvin, because this is Kelvin, right? Which means that this allows us to, if we know these pieces of information, we can solve for EA, right? Note that this being our frequency factor, not something we actually know off the top of our heads, okay? That's not something that you're expected to know, which is why this, if we take the natural log of both sides, is actually the more useful form of the Arrhenius equation, right? Here, oh my gosh, what does this look like again? Ta-da! Another straight line graph, right? Where here, if we break this down, right, we have negative EA over R, basically times 1 over T, right, plus ln of A, right, is equal to the ln of K. So if we look at this, what this means is we plot the ln of K versus 1 over T, right? So we're going to plot ln of K versus 1 over t, then my slope is going to be negative EA over R, right? Which means that as long as we have these pieces of information, we can do a plot, and we can work backwards to figure out what our activation energy is going to be. Yeah, does that make sense? Okay. In addition, if we happen to know any of these, right, we can use them like we used our other integrated rate laws and just solve for our pieces, though most often what we're doing is we're looking at graphs to deduce what our activation energy is. Okay. Thank you for listening. Be good, and I will see you soon. All right. Bye.